And what's funny is you were the first person to say it too. Okay, so we're going to talk about what's called U substitution, or what the Warner Brothers like to say as UDO.
I like it better.
Whatever, it's fine. Okay, U substitution. Do you guys feel like bright and sunny with this yellow? I know, we can't get a tear from it. But wasn't Mr. Glover handing out sunglasses in class?
Wasn't.
Who's in sin?
Used to be.
I don't know. He tweeted pictures of students with sunglasses. I didn't know if maybe he was giving them out.
To be honest.
Okay, so U substitution. So U substitution is kind of a way for us to do the chain rule backwards. Okay, let's recall what the chain rule is. If we have the derivative of a composition, then we take the derivative of the outside, leave the inside alone, times the derivative of the inside, right? So, based on our antiderivative knowledge, if we have this perfect setup of f prime of g times g prime, then its antiderivative would be that composition. Okay. Now, how many of us are going to be able to look at an actual composition of a function and be able to tell, like, bam, oh yeah, this is the backwards chain rule. Okay. It seems like it would be kind of hard to identify, okay, given different situations, and it would have to be like the perfect setup, okay? So we're going to talk about this rule, but we're going to use this method of U substitution to make it work, okay? We want to look for, when we use substitution, an integral that has some sort of composition, okay? That is going to be kind of our clue that maybe this will work. I'm not going to say that it's going to be able to work every time, but inside of our integral, if there is some sort of composition, that's kind of like a green flag, like, ooh, we should at least look into it, okay? And what's going to happen is we are going to let the inside function equal u. And what we're going to do is we are going to rewrite our integral in terms of u. So we're going to go from something that's like a function of x dx to something that's a function of u du. Okay, which is why you saw the u du on the first slide. Okay. So this is what we're going to do. Okay, I'm just going to give you the steps, and then we're going to go from there. Okay, we'll do an example. So the first thing you're going to do, if we can use this, is you're going to choose something to be u. And the best candidate for u is what's inside a function. Okay, and I will show you what I mean with multiple examples today. Okay. Okay. The next thing we're going to do is we are going to differentiate. We're going to kind of think about, well, if we were taking the derivative and we were applying the chain rule, this would happen. We have to account for that in our work. So as a differential, we are going to differentiate and then use what we did in step 1 and step 2 to go ahead and rewrite the integral in terms of the u and the du. Now, Once your integral is rewritten in terms of the u's, the whole purpose is so that you can integrate with our basic rules that we've been working on the past few days. So you'll do the integration with the u's, but since we didn't start with the u's, we will have to change them back to x's. Okay, with whatever substitution we came up with in the first place. So let's talk about the basic rules that we have. We have all of our trig rules. We have the power rule, e to the x. We have 1 over x, the natural log of x, that are linked together. Those are really all of our rules for integration that we've talked about so far. Okay? So if we cannot rewrite our integral to use one of those rules, or if the rewriting would be too out of control, then we have this to fall back on, this u substitution. Okay, so go ahead and write down this integral right here. The integral of x squared plus 1, the quantity to the 50th, 2x dx. Okay. Now, yesterday you had something on your activity. It was like x plus 3, the quantity squared dx, right? That you could multiply out and then take the antiderivative of the individual terms. Do you want to multiply this out? To the 50th? No, not even when we were doing the binomial theorem in pre-calculus, I would never make you multiply this out. Okay, that's not efficient use of time. Okay? However, do you notice how x squared plus 1 is inside the 50th power? Okay, so we have a composition, right? And it's conveniently being multiplied to a function that seems like it could be nice. All right, so this is what we are going to do. We are going to pick our inner function to equal u. So I'm going to write u equals x squared plus 1. I'll write this over here. Thank you. Okay. If we are going to change to u's, that means we also need to change the dx to be in terms of u. So what we're going to do is we're going to differentiate with differentials. Okay? So like the, I'll do this a couple different ways. Okay? If we're taking the derivative with respect to x, this would be du dx equals, what's the derivative on the right side? 2x. So du equals 2x dx is how we could write that. You remember our differentials chapter where we separated them? Okay, so du equals 2x dx. Do you see 2x dx in our integral? Okay, so this is what we're going to do. X squared plus 1, we're going to change to u. And 2x dx gets to turn into du. So our new integral becomes u to the 50th du. Can we integrate that? That's just a power rule, right? Okay, before we do that, questions on how I got u to the 50th du inside my integral?
Well, just on the right side, when we solve for du, will it always end up being what's on the outside?
But that's like where we would check to see most of
Yes, or we can manipulate to where we can. And I'll show you what that looks like here towards the end. Right now I'm going to give you examples that it's like exactly what we need just to kind of get the hang of it. Okay, so Turner asks, is it always going to be exactly what we need right here? It's not going to be. This is a nice example for us to visually see what's going on, but here in a few examples, I'll show you what it looks like when it's not exactly what we need. Okay, so when we take the antiderivative, we would increase the power, multiply by the reciprocal of that power, and don't forget your plus c. Now, this question was asked to us in terms of x, so your answer will need to be in terms of x. So for your final answer, you would go ahead and take u and rewrite it to x squared plus 1, because that is what we originally defined it to be. Okay. And just like before, if you wanted to check your work, you could take the derivative of this to see if that's what's inside the integral. You would have to use the chain rule, okay, but we would get back to that same place. Okay. Write this one down. Okay, so when I see this integral, a couple things concern me. Okay, first of all, I have cosine, but it's multiplied to something else. We've never done anything like that. Okay, also what's concerning is there is something besides x inside of cosine. Now we've talked about like the cosine of 5x or the cosine of 3x, like anything linear really is okay. But once we start putting something that's not linear inside of a function, that is when it becomes a true composition. Okay? So, do we have a composition? Yes, and it's multiplied by something extra, so that's a good sign. Okay? What is our composition that we would want to focus on? Okay, cosine of x cubed. So x cubed is inside of our cosine function. So Colby, what would we choose for you? Well, you told me okay, so you told me the composition was cosine of x cubed. So we need a piece of that. So we could choose to be x cubed. Okay, watch this. If we differentiate, we would have du equals, what's the derivative of x cubed? 3x squared dx. Are you okay with me separating du and dx right away? Okay. Well, look at this. We're going to have to replace dx, but dx here is attached to 3x squared. Do we have 3x squared dx in our integral? We do. We have 3x squared dx right there. So this integral will become the integral, this gets replaced with du, and then this becomes cosine of u. Oh, my S got kind of funky there, sorry guys. Antiderivative of cosine. Sine of u plus c. So then our final answer, we would want this to be in terms of x. So this would become the sine of x cubed plus c. I have a problem that I want you to do without me. So at your table, pod, whatever it is, work through this problem, and I want you to check answers with the people at your pod. I want you all to be getting to the same place. Okay? Not any more work than the problems we just did. Not to fear, my dear.
Okay.
Don't you lose the flex.
Yeah, is it just like the cylinder, like the size? Scroll down so you have a little bit more room.
So like yesterday we had the little integral sign like square dx, and then force in terms of x, that just like when you take it. So that's just like
Thank you for being encouraging and motivated.
I think
Yesterday it was just.
it might be true
That you
will
love
it
that.
into existence, you know? That I love that.
Okay, Grace is putting her work up on the board. It looks like she has let u equal 2x to the fourth. Okay, so she let u equal 2x to the fourth, so du was 8x cubed dx. We conveniently had 8x cubed dx, so that could be replaced with du. And so she ended up with tangent of 2x to the fourth plus c. Okay? Great. Now this has all been really nice, hasn't it? Exactly what we needed has always been in our integral in the three examples that I've given you. What happens when it's not? Stop it. Write this down. Don't give up so easily, people.
Square root.
Okay, so let's look at this. First of all, we have this square root, and under the square root is something that is not linear, and so we have a pretty hefty composition, right? And outside of the radical, there's something, which is good news, okay? So we have a composition that's multiplied to something. So, maybe this is going to work out. What would we want U to be? Okay, what is under the radical would be a great option. Okay. If you let U equal something and your du isn't really something you have in your integral, erase it and try again. Okay. So du would equal what? 15x squared dx.
Polar or close?
Elaborate on that.
It's got an x squared.
It's got an x squared dx, doesn't it? We have an x squared dx and an x squared dx. What did you say? You said something. Okay, so if we are going to replace x squared dx, we would have to move that 15 over so that we could put it in with the du to balance it out. Okay? So whatever is in the integral, yes, we need exactly that. So if you have a coefficient that's not matching up with what you have inside the integral, divide it over and then you'll have that with the du to replace. Okay, so this is going to become, okay, x squared dx becomes 1/15 du. And then the square root of 5x cubed plus 4 becomes the square root of u.
Do you have to put the 15 on the other side of the integral sign, or can you put it on the inside?
So you can put it in the inside. It would not matter. I will typically put it on the outside so that I don't have to worry about it until the very end. Okay, so you can put it inside or you can put it outside. Remember, we have that constant rule to where it doesn't matter if it's inside or outside. Okay, so now we have 1/15 times, this becomes u to the 3/2 times 2/3 plus c. So we have 2/45, 5x cubed plus 4 plus c. Oh, yeah, it does. Thank you. Okay. So U substitution, I'm giving you some pretty nice examples. It opens up a lot of doors, but it's not going to work every single time. Okay. Would it work here? Would U substitution work on this composition? Okay, what's missing? Okay, if we don't have like that G prime, right? And it doesn't have to be exactly G prime, right? We would need some sort of what right here? We would need some sort of x, whether it be 52x or 4x would be nice, right? But we would need an x over here to where when u was the inside, we would have something to be with that dx. Okay? What about this guy right here? Oh, well, let's go back. If I gave you this integral, u substitution wouldn't work. What would you have to do? We would have to multiply out the binomial, and we'd have 3 terms to take the antiderivative of. It isn't bad. It isn't. But U substitution isn't. Thank you. What about this one? Would U substitution work here?
Yeah. Wait.
There's an X.
There is an X.
So it's not have to multiply by 100. Must be X squared.
I can't finagle an X out of thin air. Okay? We can rearrange coefficients, but this is an X and we need X squared dx. We have X dx. Okay? So this one would not work. Are you kind of seeing the pattern with these polynomials? Right? If U substitution is going to work, that derivative of the inside needs to somehow be somewhere. Okay. So here again, U substitution would not work. You would have to multiply that out, and you'd have, once again, 3 terms to take the antiderivative of. One more. Okay, so first of all, we have something nonlinear inside of sine. Okay, let's grab them. What would our U equal?
X to the 6th.
And if U equals x to the 6th, we can kind of see where this is going, right? Our du equals 6x to the 5th dx. We don't have exactly that, but what do we have?
X.
We have x to the 5th dx. All right, so we could rewrite this. We could rewrite x to the 5th dx as 1/6 du. Okay, now we have exactly x to the 5th dx. We can substitute in for x to the 5th dx, 1/6 du, and so then the sine of x to the 6th becomes the sine of u. Now that's very simple, isn't it? Okay, so now the antiderivative of sine u would be negative cosine. So our final answer would be negative 1/6 cosine of x to the 6th plus c. Once again, we can check our answer by taking the derivative of that and making sure we get back to our integrand. So we will always know if we were right.
That was the last one.
That was the last one. Okay? Wow. We have 14 minutes left. Okay? Now, why am I leaving time at the end for you to work on your homework? First of all, I want to make sure that you get some practice. But this is a technique that you need to do lots of examples of in order to get comfortable. Okay? The more examples that you do, the more you're going to have some vision of where to go. Okay? So, every problem's different. Kind of like when you did trig identities. We had the same process, but every single problem was different, and you just needed to practice. Okay? So, somebody at your table, get out a book or take a picture of the book or whatever you need to do. But my expectation is that you are all working on calculus until 11:35.
Can we shut it down maybe like
No.
11:32?
No, maybe 11:34.